So today it's a pleasure to have Ethan as our first speaker, and he'll tell us about generalized symmetries, gravity, and the Swampland. Please, Ethan, take it away.
All right. Thank you very much. And thank you very much for the organizers for inviting me to talk. So I'm going to tell you today about generalized symmetries, gravity, and the Swampland. This is based on a paper that came out last July in collaboration with these folks down below. So, oh wait, there we go. And can everyone see my cursor, by the way? Okay. Yeah, so for some background, note that string theory compactifications on d-dimensional manifolds, we'll call X, lead to effective gravitational theories in lower dimensions with Newton's constant that goes as inverse of the volume of X. And while it's generally believed that there are no global symmetries in quantum gravity theories, there may be approximate global symmetries that arise in the infrared as we take the volume of X to be very large. So in our universe, you could imagine barium minus lepton number as some approximate global symmetry that is either broken or gauged in the UV. So a natural question in the context of string theory and M3 compactifications is, since these global symmetries correspond to topological operators, how does then string theory engineer these approximate topological operators for these approximate symmetries in the infrared? Conversely, if we have a bunch of non-compact spaces labeled Xi, then M theory with these backgrounds have generically some exact global symmetries. And then if we were to glue together these Xi to some sort of compact space X with some sort of finite volume, how do we read off how these global symmetries are gauged or broken? Okay, so if you don't have any time for the rest of the talk, you got to go. Then these are the rough answers to these two questions. The answer to the second question is maybe a little more obvious, which is it'll have to do with the completeness of the spectrum of charged objects in theory, which break or gauge the global symmetries. And the first question, the answer is maybe not so obvious, where these, we'll show that these topological operators, or approximate topological operators, correspond to some sort of branes on cycles of a compact space X with the singularities of X deleted in some way. Just an overview of what we're going to do. So we're going to review just global symmetries and also some of the local ingredients of M theory on non-compact K3 manifolds. And then we'll study M theory on compact singular K3 manifolds and introduce a cutting gluing method for calculating the gauge group without resolving singularities. So in the infrared, we'll see, and then in the infrared, we'll see how we get these emergent topological symmetry operators and understand how it matches to the UV definition of the gauge group, which has to do with what are the charged electric and magnetic objects. And then we'll cover two examples of K3 manifolds and then Calabi-Yau threefold manifold before coming to the conclusions. Just a very quick review of global symmetries. If we have, so we're viewing a zero-form symmetry in a d-dimensional QFT. This is equivalent to having a d-1 dimensional topological operator, and it can act on a local operator by passing through it. So in this illustration, we take the topological symmetry operator and pass it to the right, and then we have some sort of action on the local operator as well. And zero-form symmetry operators don't necessarily just have to act on local operators. They can also act on line operators, as for example, charge conjugation symmetry acts on Wilson-Tooft lines in 40 gauge theories. And more generally, a K-form symmetry will correspond to a d-k dimensional topological operator, which generically can link with some sort of charged operator, which is supported on some sort of k-dimensional manifold. And we have a similar action to as before, where now the analog of passing the operator through, passing the charged operator through the topological operator involves a linking between the charged operator and topological operator. Okay. So some local M theory ingredients we'll need. So recall that M theory on a ADE singularity just corresponds to a 70 Supring-Mills theory with a corresponding gauge algebra. This is just the usual Mackay correspondence. And this theory has a one form and four form global symmetries with a mixed Toft anomaly. And these groups are given by the abelianization of this group gamma. So for example, when gamma is just a cyclic group, the abelianization is just the same. And when gamma is, for example, the binary tetrahedral group, then the abelianization is Z3. So in this dictionary, Wilson lines with non-trivial one-form symmetry charge correspond to N2 branes wrapped on relative two cycles that have a non-trivial image in the first homology of the asymptotic boundary of the ADE space. So it's just given by this length space here. And similarly, Toft defects arise from wrapping M5 branes on the same two cycles. And the global structure of the gauge group can be chosen by choosing particular boundary conditions for the C3 and C6 potentials of M theory on the asymptotic boundary. And this is just an illustration of mostly what I just said. So here I'm drawing an M2 brane on a relative two cycle with non-trivial image in the asymptotic boundary. And I've also drawn a, so this engineers a Wilson line, which is charged in the one-form symmetry. And I've also drawn the topological operator corresponding to the one-form symmetry, which is given by an M5 brane, which is localized on a one cycle at the boundary, but does not touch the 70 physics over here. So it's topological simply because it would take an infinite time for any type of metric deformation of this M5 to ever reach the 70 observer. Okay. So now some generalities of M theory and compact K3. So at low energies, we have a 70 Supring-Mills capital gravity with a definite gauge group. So there's no asymptotic boundary to play with, so we can generate different gauge groups anymore. And I should mention that a singular K3 always has a non-zero second Betti number. So we'll have some abelian gauge factors in addition to some non-abelian gauge factors that arise from ADE singularities in the K3. So the group will, the gauge group for the 70 theory will generically look like some simply connected non-abelian gauge group mod some finite group times an abelian factor, and then modulo some additional finite group which identifies some factors from the two sides. And we'll see how the form of this group arises from two different perspectives. So first, we note that we wrap M2 branes on the second homology group of the K3. Then these give rise to electrically charged particles. So we must have that the center of G full is equal to H2 of X up to some Pontryagin duality. So namely, H2 of X will have some integer factors, because I'm considering a homology with integer coefficients. Then after I take the Pontryagin dualities, those integer factors will turn to U1s. And moreover, I could have easily wrapped M5 branes on those same second homology classes, which give rise to magnetic 3 branes. And this would tell me that pi 1 of the full gauge group ought to be, also ought to be equal to H2 of X. So somehow we must have, so then putting two equations together, we get that the center of the gauge group must be equal to the Pontryagin dual of the first homotopy group of the gauge group. So this is a non-trivial constraint. So for example, if G full were SUN, let's just say G full were SUN, then it would not satisfy this equation here. And so somehow this Z prime and Z double prime finite groups must conspire in such a way to make this condition hold. And after our paper, this condition motivated in the context of type 2B on K3s was called a maximally mixed polarization, with the idea behind the name being that the lattice of states from M2 of M2 branes and M5 branes are the same, or in other words, the electric and magnetic lattices of this gauge group are the same. So how do we calculate Z prime and Z double prime? So it's helpful to look at a Torres sequence of the K3 with respect to gluing local neighborhoods of the ADE singularities. So namely, this sequence will reduce to this four-term sequence here, where X is the original K3, X circ is the K3 of the singularities excised. And these, oh, I did this wrong. These UIs are the ADE singularities, and the partial UIs are the length spaces. So this equation down here should be a partial UI. So just in mathematical terms, we have a map that probably the most non-trivial map involves going from 2 cycles in the K3 to some collection of 1 cycles that surround the disjoint sum of length spaces surrounding each of the ADE singularities in the K3. Okay. So as a warm-up, let's try to interpret what the image of partial 2 is. So if we wrap M2s on such cycles, then we know that they must be charged under the non-abelian gauge theory factors. In particular, they're going to be charged under the center of this simply connected non-abelian group GSC, which we defined over here. So this means that if we take the co-kernel of this map, in other words, just H1 of this partial X loc, which is it's just H1 of a disjoint union of length spaces, modulo the image of partial 2, refer to electric charges that are never realized by M2 branes. So we see that since those electric charges are never realized in the 7D theory, then we must have that this Z prime factor over here is the co-kernel of this map, which namely is equivalent to H1 of X circ. And over here, I have an illustration showing a 2-cycle in H2 of X, which has a non-trivial image in H1 of partial X loc. Okay. So now to determine Z double prime, let us first define the free part of H2 of X as just H2 of X mod the torsion. Then the M2 branes that wrap elements, non-trivial elements of this group must be charged under the abelian gauge symmetries. If we look at if we go back to this map over here, if we have elements in here that are part of the free part of H2 that are non-trivial under this map, what that's saying is that certain electric particles that are charged under the U1s are also charged under the centers of under the center of this GSC. So in other words, we identify this Z double prime with the image of this partial 2 restricted to the free part of H2. And we can see, just to again recall the definition, that this Z double prime identifies some elements of the center of this thing with the U1 over here. And one can also play a similar game of arguing these conditions from wrapping M5 branes as well, which we do in the paper. Okay, so now turning to emergent symmetries in the deep infrared. Basically, we've determined what the global gauge group is in terms of massive charged particles and tensionful 3 branes from wrapping M2s and M5s respectively. But how does one tell what the global form of the gauge group is in the deep IR when the only massless degrees of freedom are just the vector multiplet? So just a quick recall is that in pure 4D gauge theories in flat space, the global forms of the gauge groups can be distinguished by this set of genuine Wilson and 't Hooft lines, where genuine means that these are line operators which do not have surface operators attached to them. So for pure gauge theories with adjoint matter, the global gauge group, the global form of the gauge group is equivalent to identifying the higher form electric and magnetic symmetries. So the case of 40, the electric and magnetic symmetries are both one-form symmetries. And then in 70, the electric symmetry is a one form and the magnetic symmetry is a 4-form. Okay, so and at low energies, we have Wilson and 't Hooft effects from M2s and M5 branes on torsion of H2. But when we consider the theory with a cutoff close to the Planck scale or the species scale, then these Wilson lines can end on heavy charged particles, similar to these 't Hooft effects on tensionful 3 branes. This is because these M2s and M5 branes, of course, correspond to some charged states. But the point is that at low energies, these can be integrated out and just lead to some sort of higher dimensional operator. So this implies that the emergent gauge symmetry in the infrared is just so I'm just restricting to torsion here for simplicity, is the torsion of H2 for the one-form symmetry and the torsion of H2 from the 4-form symmetry. And moreover, we prove in the paper that there's a perfect pairing between the torsion of H2 of X and H1 of X circ, where we've deleted the singularities. And this motivates by identifying the electric, the topological symmetry operator for the electric symmetry with an M5 brane wrapping a 1 cycle in H1 of X circ. So this gamma 1 circ is a member of this. And alternatively, we identify the topological symmetry operators for the emergent symmetries with M2 branes wrapping these 1 cycles. And note that these are not exactly topological symmetry operators. Otherwise, we would have some sort of global symmetries in a quantum gravity theory. Because volume of X is large, but non-zero. So this argument I said way back at the beginning of the talk so way back over here, when we had a non-compact manifold, if we have some sort of M5 wiggling over here, the only reason why it was topological for a 7D observer was because the distance between these two things was infinite. But now when volume of X is finite, then that distance is no longer infinite. And also, moreover, these are not even stable objects because H1 of X is 0 for all K3 manifolds. So these topological operators can, or these semi-topological operators can end. So just quickly reviewing some examples. So in K3 is a T4 mod Z2. The Meyer-Vera-Torres sequence looks like this. And applying the techniques you said previously, this implies that the full 70 gauge group is of this form. And this agrees with previous studies of heterotic on T3 and using duality to M3 and K3. And moreover, a more complicated example is we can have T4 mod binary dihedral group Note that there's actually two actions of the binary triangle group on T4. We list the case for both in the paper, but we'll just choose one for the sake of the slide. In that case, the Meyer-Vier-Torres sequence looks as so, and based on just from exactness of the Meyer-Vier-Torres sequence, you can extract that the full gauge group has this form, and this actually agrees with one of the entries of this paper over here, which gave a exhaustive or mostly exhaustive survey of the global forms of the gauge groups for heterotic on T3. Okay, and then to hopefully mention a Calabi-Yau threefold example of T6 mod Z3. So this space has 27 singularities that look like C3 mod Z3, which means that at low energies, we've engineered 27 copies of a 5D SCFT known as Seiberg's E0 SCFT, although I guess it should be called Seiberg-Morrison's, but okay. And up to discrete gaugings. And then each of these CFTs has a higher form symmetry, a Z3 one form symmetry and a Z3 two form symmetry. And we can just play our game of calculating the homology of this space, and we catalog how, given that the zero form gauge group of M theory on this space is like this, and the one form gauge group is like this, we show how exactly each combination of these one form and two form symmetries are gauged or broken. Yeah, I should also mention we also list the full two form symmetry gauge group as well. Okay. So to conclude, for M theory compactation case 3, we've shown that the global structure of these 70 gauge groups emerges from cutting and gluing local patches of this K3 and shows how this is, and we showed how this is consistent with the expectations of the higher form symmetries of each of the local patches. And we've also shown how the emergence of topological symmetry operators in the infrared coincides with the emergence of some approximate global symmetries. So it'd be interesting to generalize this procedure to more complicated Calabi-Yau threefolds, where you can have, for example, singularities of different codimension. We study one example in the paper of T6 mod Z4, which does indeed have singularities of complex codimension 2 and 3, but I think there's probably more to say there, and also definitely more to say about possible F theory uplifts. And one question that this seems to raise is that, is there an anomaly that guarantees that the rank 22 gauge groups for all 70 n is equal 1 supergravity theories have this precise form that we showed earlier of this of the Z prime and Z double prime having the forms, or I should say, should it always be that the center of the full gauge group is equal to the Poincare control of the pi1? So there's no clear anomaly why that should be, but all M theory examples seem to give this. And then these emergent topological symmetry operators can in general be non-invertible. So what does M theory have to say on how these would reduce to invertible symmetries, which we expect to happen in quantum gravity theories due to gravitational solitons? And lastly, a natural generalization is related to generalizing this dictionary to M theory on K3 with frozen singularities, which could also inform this question over here for lower rank gauge groups. Yeah, thank you for your attention.
Thank you for the talk. Are there any questions? Oh, there's a question here from Alec. Maybe we start with that one quickly.
Okay, can you hear me?
Yes.
Okay, thank you for the nice talk. I have two questions about the maximally mixed polarization condition. So the first one is that the necessary condition to make sure that the existence of charged objects violate the higher form global symmetry? And the second question is that, I mean, you commented that you see this in M theory, but like, do you have counterexamples to it? How general do you expect it to be?
For M theory and K3 with no frozen singularities, there's no counterexamples. So in the you know, I talk about some examples of Torres of quotients of T4, but that condition is true for all K3s.
And the first question, is that the necessary condition for, like, to make sure that the charged objects, like the completeness essentially guarantees the lack of global symmetries?
Oh, I mean, in general, like if you go to like Calabi-Yau threefold compactifications, you wouldn't expect a maximally mixed polarization there, and you also don't expect global symmetries. So for K3s, it seems to always be the case. I don't see clearly how it's related to the lack of global symmetries, but yeah.
Okay, thank you.
I think there's a question in Munich.
Hi, Ethan. Can you hear me?
Yes.
Yeah. Okay. Hi, it's Ivano. Very nice talk.
Hi.
So I was wondering about the approximate topological character of these operators, right? Usually it's possible to quantify this by by the violation of the word identity on let's say a sphere of some radius, and then you look at the dependence on the radius, stuff like that. Have you looked at this, or like how this depends on the volume of the internal space, something like that? Like you should give.
Yeah, I mean, we suspected something like this analysis can be done, but we didn't really look at it other than saying, oh, okay, well, our corrections are like 1 over m Planck or something. But I agree. I mean, an interesting, related to that would be that this sort of non-topological nature of these operators is also related to the long lifetimes of certain objects. So if, for example, these cases don't really have an easy thing to look at, but if you imagine that you have an emergent symmetry, like an emergent one-form symmetry, that is also not spontaneously broken, then you would have some sort of string at low energies, and then you can ask, what's the lifetime for which this string can nucleate or right, can break. So I think your question is also related to something like that, and that would be pretty interesting to do in detailed examples.
Yeah. Thanks.
All right, if there are no further questions, let's thank Ethan again.